This is slide number 68 and I am your presenter Asloob Mudassar. We are going to discuss today matched filters in character recognition problems, or you can say matched filters in pattern recognition problems. So let's explain the problem, what is the problem and how we are going to solve that problem. Assume that there are n inputs labeled by O1 star, O2 star, O3 star and so on up to On star. This star means that this is actually the conjugate of the object O1, conjugate pattern of object O2, conjugate pattern of object at O3 and so on up to the conjugate pattern of capital N. So these are the n objects. I am not saying a conjugate again and again, but I shall be using the word star. So O1 star, O2 star, O3 star and so on up to On star are the n inputs, and these inputs appear sequentially at the object plane of a coherent processor in random order. So you see that we are placing one input at a time. So single input will appear at one time. Once this input is processed, then you know that the second input can be placed. So the order could be sequential and the order could be in order or maybe out of order, but you know that we can place these n inputs. We want to build a character recognition machine which can help us to identify which of the inputs has appeared at the object plane. So it means that if you place any input object on that machine, we should be able to recognize that which input has been placed as an input in the machine. We need to construct a frequency plane filter consisting of matched filters. We need to construct a frequency plane filter. So look at this is very important point. So what we are going to do is that first we are going to construct a frequency plane filters. You know that we have discussed two types of frequency plane filters earlier. One was the van der Rohe filter and other was the joint transform correlator. So we need to construct a frequency plane filter consisting of matched filters, each of the individual input. So our frequency plane filter should be such that it should include or it should incorporate matched filter of all the n inputs we have mentioned above. And you know that when we are talking about the matched filter, it means that capital O1 star, capital O2 star, capital O3 star and so on up to capital O and capital N star. What are these? These are actually the complex conjugate of the spectra of the object O, small object O1, small object O2, small object O3 and so on respectively. So capital O are the spectra of the corresponding images that we have shown above. So we need to construct a frequency plane filter consisting of matched filters, each of the individual input, that is O1 star, O2 star and so on up to N star, as a single frequency filter. So it means that we are going to make a frequency filter that contains the frequency plane filter of each of the individual input that we have shown. That is, we are recording the complex, we are recording the Fourier transform, that is, we are recording the spectra of the inputs. In principle, the conjugate of the spectra of the inputs we have shown above. And all these inputs are recorded as a single frequency filter. However, in the construction of such a filter on a single frequency, on a single transparency, the carrier wave, which is we call the plane wave here, must be different each time. That is at angles theta 1, theta 2 and so on up to theta n, where theta I is the plane wave angle at the Fourier plane during the storage of OI star. So recording OI star, that's capital OI star, as a function of theta I will ensure the autocorrelation peak at the image plane to be distinctly located when matched filter input appears at the object plane of a coherent processor. So you see that we want to record over the frequency. Recording of the frequency plane filter is the main task. So we shall present one input, for example small O1 star, and then its spectrum, which is capital O1 star, will be recorded. But you know that in the recording we are using the plane wave from the as a reference wave at the Fourier transform plane. That plane wave has an angle theta 1. So when we are going to record another, when we are going to record capital O2, the capital O2 star, we are using the plane wave at an angle theta 2. Similarly, for the capital O3 star, the plane wave angle should be theta 3. So it means that for each recording of these spectra, that is a conjugate spectra, we are going to change the angle of the plane waves at the Fourier transform plane. So once all these inputs are recorded, then you know that we have to remove over a glass plate or the photo glass on which we have recorded these, and then we have to develop that one, we have to fix that one, we have to dry that one, and then our filter will be ready. And that filter we can call it as a frequency plane filter. So that frequency filter will be used at the system which we are going to explain. So this is our setup that we are going to record over a frequency filter. So let me read the caption: recording process of individual matched filters on a single transparency with plane wave multiplexing. Plane wave multiplexing means that we are changing plane wave each time we record the matched filter of one individual input. So first of all, let me explain the setup. You have a point source in front of the lens L1 at the front focal plane. So it means that the lens L1 will generate the plane waves outgoing towards the right side. So the plane waves will illuminate two things. One is the part of the plane wave is incident on the lens L3, which the lens L3 is focusing the plane wave at a point as shown, where we have placed a pinhole assembly so that we can filter the plane wave, and we can if there are any distortions there, those are removed, and we can have a clean beam outgoing from the pinhole assembly. But look at the lens L3 and the pinhole assembly are mounted together on a single stage, and this stage can be moved up and down. Okay, L3 and pinhole assembly are moved together, but you know that they are moved in such a way that the L3 will receive the plane wave from the lens L1. So you see that after this pinhole assembly, the light will diverge and will be incident on the lens L2. All the distances are f in this case, and the L2 lens has also a focal length equal to f. So the lens L2 will generate the plane wave from this diverging wave incident on that one, and you can see that the plane wave is inclined at some angle. It is because the diverging wave which is hitting to the lens L2 is hitting the lens not at the optical center but away from the optical center. And since the diverging wave hitting the lens L2 is away from the optical center of the lens, so it means that the lens will generate the plane wave at some angle, and this plane wave will reach at the Fourier plane. So when we move the L3 and pinhole assembly up and down, then you know that we can change the angle of the plane wave outgoing from the lens L2. So this is the way that we can do the plane wave multiplexing, just by changing this assembly, that is the assembly of L3 and pinhole together, because they are fixed together. So you see that the plane wave multiplexing can be achieved just by moving the L3 and pinhole assembly up and down together. Okay, now let's come to the plane wave outgoing from L1. The other part of the plane wave is illuminating the object. single object at a time. So a single object will appear just before the lens L2, that is, the objects are appearing at the front focal plane of the lens L2. So so the objects are placed in such a way that only one object appears in the optical system, because we have a roll of films with the negative of the object, and we can pass these objects one by one by rotating the film roll. So once this object is placed, which is at the front focal plane of the lens L2, the light will pass, the diffraction will occur at each object plane, and the diffracted wavefronts will be received by the lens L2, and L2 lens will generate the Fourier transform of each object at its back focal plane. Since this plane wave is also off axis from the center, that is located off axis from the center of the lens L2, so you know that the projected Fourier transform also is also making some angle at the Fourier plane. So we have the Fourier transform of the object appearing at the back focal plane of the lens L2, and also the plane wave coming from the lens L2 is also incident together. So these two waves, that is the plane wave and the Fourier plane and the Fourier transform of the object, will interfere each other, and you know that one matched filter is recorded. But for the next matched filter corresponding to the next object, we shall replace the object by the next object in the queue. So next object will appear, and at the same time we shall change the L3 and pinhole assembly with a precision by some angle, so that we can generate the plane wave angle. So the plane wave angle will be changed for the second object. Similarly, for the third object, once this illumination or this exposure of the photographic plate is recorded, then you know that we shall move the third object. So the third object will be placed in the setup, and then you know that this L3 and pinhole assembly will be moved precisely to another position, so that the angle of the beam of the plane wave outgoing from the L3 and reaching the Fourier plane will be changed. So each time we place the object, the angle will be changed, and of course due to the interference we are recording the matched filter corresponding to the third object. And similarly for all these n objects, one by one, by changing the angle of the plane wave, we shall be recording all the matched filters on a single photographic film. So once we have recorded all these matched filters corresponding to the inputs that we have placed just before the lens L2, we are going to remove the glass plate. We shall develop the glass plate. We shall fix the glass plate. We shall dry the glass plate. Then that glass plate will act as over matched filter or frequency plane filter. So that frequency plane filters will be used in the next setup, and if we place any of these input objects, we can recognize which of the object has been placed. Now let's explain this in words. Description of character recognition machine is now given. The first step is the construction of a single frequency plane filter that must contain the matched filter for each expected input to be recognized. The construction of a frequency plane filter is explained in the figure above. The individual object slides are placed one by one in the path of a plane wave. The lens L2 generates the Fourier spectrum of these slides at the photographic plate, which we call as photoglass. A carrier or the reference beam is added. The angle of the reference beam is chosen to be different for each input OI placed at the zeta eta plane. L3 plus the pinhole assembly is mounted on a platform which is moved up or down to set different angles of the reference beam. An angle theta I is set for the input object OI. If the matched filter corresponding to an input OI is to be recorded, then in the recording process an object with amplitude transmittance equal to OI conjugate with at coordinates minus zeta comma minus eta is placed at the object plane. So you see that this is very important point. Actually, we want to record the matched filter. What is the meaning of a matched filter? Matched filter means we want to record capital O1 star, capital O2 star, capital O3 star. So we want to record these as the matched filters. To record O1 star and O2 star, what we need to do is that we need not only the object to be placed, that is, we don't want the object OI to be placed, but in principle the object OI star, that is OI star, at the position minus zeta and minus eta should be placed at the object plane, so that we can record the matched filter corresponding to this OI, which will be capital OI star. That is the spectrum of this one, and the spectrum of this one, which is capital OI star, at the frequency plane will be recorded as the matched filter. In the recording process, plane wave angular multiplexing is used. That is, all the plane waves are identical but differ in angle theta I, where theta I is the angle the reference plane wave makes with the normal to the Fourier plane. The photographic plate, that is the photoglass, is held stationary, and the matched filters capital OI star with a frequency at the Fourier frequency fx, fy are recorded corresponding to the input OI placed at the zeta and eta plane. And you know that not only OI is placed, but OI star, that is small OI star, at the minus zeta and eta coordinates are placed at the input object. The developed photographic plate then acts as the frequency plane filter, consisting of O1, capital O1 star, capital O2 star, and so on up to capital ON star. The next step, that is, we have recorded all these matched filters on the single photographic plate. The next step is to use this matched filter in the character recognition machine given next. One of the possible inputs OI, which is located at the zeta and eta plane, is presented to the machine at the object plane. So you see that now we have recorded the matched filter on a single glass plate containing the matched filter of all these capital OIs, that is O1, capital O1 star, and so on up to capital ON star. So these matched filters have been recorded on a single plane filter. Now we have also developed these single plane filters so that they become filters actually. So we can place these matched filters over there in another setup, and then we shall present the setup with the inputs OI at the coordinates at the plane zeta and eta. So let's explain that machine. So this is the machine, you see. So let me explain the optical step. This is the character recognition machine based on matched filtering. So again, a point source is located at the front focal plane of the lens L1. It means that the beam outgoing on the right side of the lens L1 will be a plane wave. So a plane wave is going towards the lens L2 from the lens L1. And you know that we just close to the lens L1 we have placed a film of roll, so that we can bring one input at one time in front of the lens L1, and we have represented that input as small OI as a function of zeta and eta. So one of these objects will be placed one by one, but only one object will be placed. So you see that this object that we shall place will be illuminated by the plane wave, and that plane wave will be received by the lens L2. So it means that the diffraction will occur at the object plane, and those diffracted orders will be received by the lens L2. So the lens L2 will generate the spectrum or the Fourier transform of this small object OI at its back focal plane, which we call as the frequency plane. So you can see that the frequency plane can be seen containing different dots of light in the frequency plane. So this is the spectrum of the input object that has been generated by the lens L2. And you know that this is the plane where we shall place our frequency plane filter or the matched filter that we have constructed using the previous setup. So we have already placed our filter over here, and now that filter has been exposed with the spectrum of the input object. So the filter is there. Now this filter has been illuminated with the spectrum of the input object that we have placed just after the lens L1. And you know that what will happen at this plane? If the Fourier spectrum matches with one of the matched filter in the frequency plane, then you know that corresponding to that one, a plane wave will be generated. That plane wave will be received. You know that when the plane wave is generated, it means that all the phase factors corresponding to the inverse Fourier transform will be cancelled out automatically. So that plane wave will reach the lens L3. The lens L3 will generate the inverse Fourier transform of that plane wave, and that plane wave will then be focused at the image plane. So if there is a sharp focus at the image plane at some location corresponding to the reference angle that we have used in the previous setup in making that particular matched filter, then you know that we shall get a sharp point at the image plane corresponding to that location, and the other points will be where corresponding to other matched filter. The other points will be reduced in phase and has been shown as gray points in the image plane, whereas the sharp focus with the dark spot is the point which is matched with the spectrum of the input object and has been recognized by the machine and has been focused as a sharp light source at the image plane. And this point, the sharp point, will be referred to as the autocorrelation peak because it has matched with the filter, that is the spectrum projected by the lens L2 of the object OI at the Fourier plane, at the frequency plane, has been recognized, has matched with one of the matched filter over there, and then the plane wave has been generated. That plane wave is free of any phase factors or phase distortions, so that plane will be exactly focused at the image point, and that point which will give you a peak at the image plane will be recognized as the autocorrelation peak. And whereas since many matched filter has been stored at the frequency plane, so you see that at the locations of the other matched filter, some other data will also be generated, but that will not be tightly focused. So that will be focused diffusely, and blur point source will appear according to the positions of the other matched filter at the image plane, which we have shown in the gray, and those will be referred to as the cross correlation peak. So I think that the setup is now explained. So let's explain this setup in words. The filter is illuminated by the spectrum of the input object, and one autocorrelation and n-1 cross correlation peaks are detected at the image plane. The autocorrelation peak, being the sharpest and the highest in intensity, can be used to identify the unknown input at the object plane. For another object, the location of the autocorrelation peak will be different, giving a footprint of another object. The machine works only for the known objects. So it means that the known objects mean that we have used the inputs over here, all the inputs, in order to generate over frequency plane filter or the matched filter. So these inputs are said to be known inputs which we have stored as matched filter in using this setup. So this is what we mean from the known objects. So known objects, that is the objects for which which we corresponding to those objects we have stored the matched filter. Those objects will be referred to as the known objects. The matched filter based coherent processor is highly sensitive to scale, size and rotation. A small variation in the size of the input object or objects with respect to one stored as matched filter, or a smaller angular shift in the presented input with the same size will result in a drastically reduced signal to noise ratio. So you see that our object should have the same size and the same orientation when we place at this machine. However, the placement could be different with respect to the lens L1. So these objects could be placed at different location in corresponding to the lens L1, but you know that they should be placed in the same orientation. So the orientation must be the same, no rotation and no scaling, no change in the size should be there. So the same object with the same size should be placed, and the placement, if there is errors in the placement, that would not be problematic, because according to the shift theorem, the Fourier transform of that shifted object will be the same as the object placed at its original position, except that some phase factor will be multiplied, and that phase factor will not be any problematic in this case. So the matched filter based coherent processor is highly sensitive to scale size and rotation. A small variation in the size of input objects with respect to one stored as matched filter, or a small angular shift in the presented input with the same size will result in drastically reduced signal to noise ratio. A matched filter containing storage of different sizes of same object. A matched filter containing storage of different sizes of same object and with different angular aspects of the same object may give a better signal to noise ratio, but the use of such a matched filter in practical applications is unsatisfactory. There is a need to discuss coherent systems which can better handle the object size variation and rotation of the object. So you see that in the system that we are presenting, we require that the object size should be the same for which the matched filter was stored, and the object when placed in the setup, in this setup, the object size should be the same. However, the location of the object could be different with respect to lens L1. No rotation, no change in size is required for the object to be placed in this setup or in this machine. And if you see that we have here in this paragraph, we have suggested that we should store different sizes of the object, or we should store different angular rotation of the object, and then we that is matched filter, that is in the storage of the matched filter all possible sizes of the object and all possible orientation of the or rotation of the object should be stored. But you know that such a matched filter cannot work practically, and the performance will be unsatisfactory. So for this case, we are storing the objects with the same orientation and with the single orientation, with the same size and with the single orientation. And similarly, we are projecting this machine with the objects having the same size, for which we stored the matched filter, and having the same orientation for which we stored the matched filter. So the object should be presented to this machine in the same size, in the same orientation. However, only the provision that we have is that the object placement could be slightly different with respect to the L1. But the object should be completely illuminated by the lens L1. Okay. The matched filtering based application are however insensitive to the translation of input object on the object plane, and the strength of the correlation peak is not affected with the translation of the input object on the object plane, because the translation of an input object at the object plane does not result in the translation of its Fourier spectrum at the Fourier plane, according to the shift theorem. One of the many possible techniques is to use an extension of optical system before the object plane of a coherent processor that could be used to magnify or to demagnify and to rotate the input object for all possible sizes and rotations, and then to look for the correlation peak at the image plane. Such methods are very time consuming and at the same time less precise and less reliable. Some of the digital image processing based methods for size and rotation invariance can be adopted for optical implementation provided the optical methods are superior to their digital counterparts in the presence of parallel processing of data in optical domain. Some of these methods will be described next. So this is the end of slide number 68.